We are now going to discuss the numerical technique of taking the derivative of a function. We begin with the Taylor series. We expand the function f about some value x sub I to get f of x sub I plus 1. We then get the Taylor series expansion to be f of x sub I plus 1 is equal to f of x sub I plus f prime x sub I times h plus f double prime x sub I over 2 times h squared, and so on and so forth, where h is the difference between x sub I plus 1 and x sub I. It's also called the interval size. If we move the term on the left-hand side to the right, and we move the second term on the right-hand side to the left, and multiply everything by -1, we obtain the following expression for f prime of x sub I. The higher order terms are terms involving powers of the interval h greater than or equal to h raised to the power 1. This is your error term. Thus, we see that in order to reduce the error, the value of h must be as small as possible, or we take the limit of this function as h approaches 0. This is your expression for taking the numerical derivative of a function. Numerically, we take h to be a very, very small number. While this improves the accuracy of the calculation, the computation time actually increases because you have more intervals with smaller values of h. This type of differentiation is called the first forward divided difference. It's called the first because you are taking the first numerical derivative. It's forward because you are solving for the derivative of a function at x sub I using the function at x sub I and x sub I plus 1. In contrast, you have the first backward divided difference. This technique solves for the first numerical derivative of the function at x sub I using the function at x sub I and x sub I minus 1. The derivation of this equation is precisely the same as in the previous slide, except that a negative sign is introduced in the odd terms of the Taylor series. Or you replace h by negative h. The order of the error is again to the first power of h. And therefore, this technique has no unique advantage over the forward technique. Note that when taking the numerical derivative using this technique, you lose one data point. To get one data point of the numerical derivative, you need two data points from the original function. Thus, if you have 3 data points and you get the derivative of these 3 points, you are left with 2 data points. In general, if you have n data points, the derivative will have n minus 1 data points. You actually lose the last term in the forward divided difference and the first term in the backward divided difference. If we now take both expressions for the forward and backward divided difference and subtract the backward from the forward, you get this third equation. We then move all terms in the right-hand side to the left-hand side, except for this first term, which is the derivative term. Some terms cancel out, and these terms are those with even powers of h. We are then left with an expression for the numerical first derivative of f of x sub I from the function at x sub I minus 1 and x sub I plus 1. Notice that the error term is of the second power of h. This means that you can use a larger interval or a larger value of h in this first center divided difference technique. The disadvantage is that you lose 2 data points, the first and the last, after performing the numerical derivative. Now let's take a look at this example. The example states Use forward and backward difference approximation and the center difference approximation to estimate the first derivative of the function f of x is equal to negative 0.1 x to the fourth minus 0.15 x to the third minus 0.5 x squared minus 0.25 x plus 1.2. At x equals 0.5, using a step size of h equals 0.5. Repeat the computation using h equals 0.25. Okay, we note the derivative can be computed directly as f prime at x equals 0.5 equals, so we take the derivative now, negative 0.4 x cubed minus 0.45 x squared minus 1.0 x minus 0.25, and we let x be equal to 0.5, the derivative at x equals 0.5 gives us negative 0.9125. Let's begin with the step size of h equals 0.5. If h equals 0.5, then we need two more data points. Let's say x sub I is equal to 0.5. Then x sub I plus 1 is equal to 1, since h equals x sub I plus 1 minus x sub I. Also, x sub I minus 1 is 0 because h is also equal to x sub I minus x sub I minus 1. Remember that h is the interval size or the step size. Now the function f at x sub I minus 1 is equal to 1.2 using this expression that we have here. The function f at x sub I equals 0.5 is 0.925. The function f at x sub I plus 1 is equal to 0.2. We can use these values to compute the forward divided difference. F prime x at x sub I is equal to f prime at x sub I plus 1 minus f sub x sub I plus 1 divided by h. F of x sub I plus 1 is 0.2. F of x sub I is equal to 0.925 and h is equal to 0.5. This gives us negative 1.45. If you compare that to this value, we have an error of about 60%. Using the backward divided difference, we have f prime x sub I equals f of x sub I minus f of x sub I minus 1 divided by h. So that's 0.925 minus 1.2 divided by 0.5. This gives us negative 0.55, which gives an error of about 40%. Using the center divided difference, f prime x sub I is equal to f sub x sub I plus 1 minus f of x sub I minus 1 divided by 2h. We then get 0.2 minus 1.2 divided by 2 times 0.5. This gives us negative 1 with an error of about 10%. You see that by using the center divided difference, the error is much smaller compared to the forward divided difference and the backward divided difference. Now let's use h equals 0.25. If x sub I is equal to 0.5, then x sub I plus 1 is equal to 0.75 and x sub I minus 1 is equal to 0.25. This gives us, for f at 0.75, the value of 0.63, 63, 28, 13, and at f at x equals 0.25 is equal to 1.10351563. If we use the forward divided difference, the derivative gives us negative 1.155, giving us an error of 26.5%. The backward divided difference technique gives us negative 0.714 for the first numerical derivative, or with an error of about 22%, while the center divided difference gives us a value of negative 0.934 for the first derivative, giving us an error of 2.4%. Notice that if we reduce the step size, all of the errors are also reduced. Also, Consistently, the center divided difference has a much smaller error compared to the errors from the forward divided difference and the backward divided difference techniques. We can also solve for the second forward divided difference. Let's go back to our expression for the first forward divided difference. If we replace the step size from h to 2h, this means that we will take the value of the function at x sub I plus 2. Because this is now 2h, we replace the step size from h to h. If we now multiply the expression for the first forward divided difference by 2, and then subtract this from the top expression for f of x sub I plus 2, we get the following expression. Let's also move all terms in the right-hand side to the left-hand side except the second derivative term and divide everything by h squared. We then obtain this expression. Notice that the last expression solves for the second numerical derivative of the function f directly without taking the first derivative first. In this process, you also lose the last two data points. The error term is of the first order, which is also good. Imagine if you take the first numerical derivative of the function twice, the error would propagate from the first to the second derivative and would be larger. This method is called the second forward divided difference. You can also get an expression for the second backward divided difference by going through the same process as the forward case, but instead replace h with negative 2h to get the value of the function at x sub I minus 2. Use the first backward divided difference expression as well. Move terms around and then end up with the final expression for the numerical second derivative as shown. The error term is also the order of the first power of h, and you also lose the first two data points. The center divided difference utilizes both first forward and first backward divided difference expressions. In this case, you lose the first and the last data points, but the error term is now in the order of the second power of h. You can further derive the expressions for the nth forward divided differences as shown, as well as expressions for the nth backward divided difference with errors still in the order of the first power of h, and even expressions for the nth center divided difference with an error in the order of the second power of h. I hope that you've understood the process of taking the numerical derivative and its advantage and disadvantages. If you've noticed, I didn't talk much about how to implement this in MATLAB or Python, since the process is pretty much straightforward. To figure out the process is the task that you need to accomplish. You should be able to begin working on machine problem 2, which involves numerical differentiation of a function. You can always ask your questions via email or in our Zoom meeting or Google Meeting sessions. The next lesson is on numerical integration.